Hello, everyone. Thank you for joining us today for our webinar, Does This Seem Off? GC-MS Techniques for Off Flavor, Off Odor, and Flavor Scalping Analysis. This webinar will be hosted by Jamie Willems and Lily Zaffas of Eurofins SFA Laboratories. I'm Amy Knock, and I'll be moderating this webinar. Before we begin, I'll let you know more about how this webinar will run. The webinar is being recorded and the slides and recording will be available for you within 3 business days. A short Q&A session will follow the presentation to answer viewer-submitted questions. During the webinar, you can submit questions you have using the webinar sidebar menu. Select the Questions tab, type in your question, then hit the Enter key on your keyboard. Remember, you can submit questions anytime throughout the webinar. And now, at this point, Jamie and Lily, I will turn it over to you to begin the presentation.
Well, thank you, Amy. As mentioned, I am Dr. Jamie Willems, and today, alongside Lily, we are going to be presenting on our approach for off-odor and off-flavor analysis in foods, ingredients, and related products. Okay, so in this presentation, I'm going to start with a bit of an introduction as to off-odors and off-flavors, where they come from, why they're important, and what we can do to address these issues. Following this, I want to give a bit of background on the analytical techniques we employ in order to analyze for these off-odors and off-flavors, followed by some case studies to give you some real-world examples of how this approach can be employed on complex samples. So, as I'm sure you're all aware, aroma and taste are important components of consumer appeal, and together they make up the flavor of a product. And the flavor of a product, alongside its other sensory characteristics such as its color and its texture, are important parts of a product's identity. In addition, aroma and taste are important components of new product formulations. Perhaps you want a new product to stand out from the rest, or in some cases, for instance, say you're making a diet product, you want to closely match the flavor of the new product to the original full-calorie food product. In addition, aroma and taste can be important parts of quality assurance. And off-odor and off-flavor can be signs of a potential problem in processing, storage, and so on. And I'll get into that in more detail in a couple of slides here. As well, aroma and taste are important parts of consumer trust. So when a consumer purchases a product, they want to know what they're getting. So for example, if someone was to purchase a product, say here in Wisconsin, and then go a few states over and purchase the same brand and the same product, they want to know that they're getting the same overall flavor across different stores and different retailers. And so when a product develops an off-odor or off-flavor, this can be very detrimental, as they can be off-putting to consumers and can prevent repeat purchases. In addition, they may be a sign of potential problems. That is, there's an underlying issue that's causing this off-odor or off-flavor. And so there are a number of factors that can negatively impact product flavor and aroma. So I'm just going to go into a few of the major classes of these factors. The first one I want to talk about is packaging failures. And this can come in a variety of forms. One of these is flavor scalping. In flavor scalping, what we have is the packaging is absorbing flavor compounds from the product over time. So the longer a product is stored in this packaging, the more of these flavor compounds are absorbed by this. And this can be a problem with plastic-based materials. And so over time, what you can get with flavor scalping is a muting of the overall flavor profile. That is, it becomes less intense. In addition, you can also get a shift in the flavor profile with flavor scalping, as certain compounds will be absorbed more readily by the packaging material than others. And the reverse can also happen, where materials from the packaging are leached into the product. This can occur if, for example, the packaging wasn't properly cleaned after production and maybe there's still some chemical residue, or the packaging used is incompatible with the product, and so it's starting to be degraded or broken down by the product. In this case, you can get leaching into your food product, which can lead to off odors and off flavors, and in some cases include harmful chemicals, say cleaning agents. As well, packaging failures can come in the form of a breakdown of the packaging. Maybe it was damaged during transport or storage, which would cause the food product to be exposed to the environment, perhaps leading to chemical or microbial contamination, which I will talk about next. So another common source of off flavors and off odors is chemical contamination. As I mentioned before, this can be related to packaging failure, where the packaging has a break or isn't properly sealed, and therefore you're allowing access to the outside environment. As well, chemical contamination can come from storage issues. So for example, if you store large amounts of product in tanks, you can get leaching from these tanks. Maybe there's an incompatible coating on the inside, or they weren't properly cleaned from what they were holding previously. You had a different product in that tank before, now you can get cross-contamination between the old and the new. As well, chemical contamination can come from improper cleaning. As I mentioned before, if you very similar on a processing line, if you had an old product that you made on there and didn't properly clean, you can get cross-contamination. However, another common source of chemical contamination is from cleaning agents. We actually see this fairly commonly. So for example, during the cleaning of a packaging line or a processing line, if the cleaning agents used, the detergents, aren't fully rinsed off, these can then leach into the product, resulting in an off odor or off flavor. As well, contamination can come from an ingredient issue. Perhaps one of your ingredients is contaminated from a different source, or you, say, for example, have changed supplier, and now you just have a change in the overall profile or flavor of your ingredient and therefore your product. Related to chemical contamination, we can also have chemical spoilage. So for example, over time, a very common source of chemical spoilage is lipid oxidation or lipid breakdown. And this is where your fats break down over time. And this can lead to off odors such as rancid, old, stale, and sometimes even barn-like off odors. And this can occur if your product is exposed to excessive light or oxygen, as well as heat, and will occur over time. Another source of off odors and off flavors is microbial contamination. Microbial contamination can come from a variety of different places, such as improper storage. For example, a product that should be refrigerated is kept at room temperature too long during storage or transportation, which can lead to microbial growth and off flavors. Improper handling can also lead to microbial contamination. One example of this is poor employee hygiene, people not properly washing their hands, not wearing their proper equipment during the production. Cross-contamination can lead to microbial contamination. For example, exposure of a product that isn't meant to be cooked to a product that is meant to be cooked can lead to contamination over time. And finally, another source of microbial contamination is a process failure. For example, incomplete pasteurization, leaving microorganisms alive in the product, which then grow over time, resulting in spoilage. And microbial contamination can lead to off odors and off flavors, such as fermented type flavors. Sharp or sour or acidic off flavors are fairly common with microbial contamination. And it should be noted that both chemical and microbial contamination can occur both during processing, packaging, transportation, and storage of this product, as well as on the consumer side. So once a consumer purchases a product, if they don't store it properly, they can also see chemical and microbial contamination. And this isn't necessarily a failure of your process, but rather a consumer issue. Finally, one other major source of off odors and off flavors in products is changes or issues in production. So this can be an issue such as a process failure. So as I referred to in microbial contamination, maybe your pasteurization is incomplete, leading to off odors due to microbial growth. This can also come from equipment failure. So perhaps your oven wasn't calibrated properly, and now it's not baking to a high enough temperature, and you're not getting those nice baked aromas and flavors that you would normally associate with a baked product. This can also be even just simple changes in production. As I mentioned before, maybe you've changed an ingredient supplier. Maybe there's nothing wrong with the ingredient, but its profile is a little bit different than your old supplier, which would just result in a shift of your overall flavor profile. And so sometimes even small changes or tweaks can have an impact on your final product. And so there are a wide variety of sources of off odors and off flavors. And so how do we approach trying to determine what is causing an off odor and where it comes from so that the problem can be traced and hopefully corrected in the future? Well, we do this through aromatic profiling. That is, we look at the profile of volatile compounds in the product. When I talk about volatile compounds, I'm talking about chemical compounds which are found in the gas phase even at lower temperatures. In this way, they can reach the human nose where they are detected. And you would be surprised at how sensitive the human nose can be to certain smells. For example, small sulfur-containing compounds can be detected down to parts per billion by the unaided human nose in some cases. So even small concentrations of off-odor causing compounds can result in a change, an undesirable change in a product. And so we examine the volatile profile of a product to look for potential off-odor causing compounds. So we look at the profile of a product, which we sometimes refer to as a fingerprint, and use this to determine potential sources of off odors. And it's important to note that currently thousands of different flavor active compounds have been identified by scientists. And when we're talking about food products in particular, we tend to have dozens or even hundreds of different compounds contributing to the overall profile of a product. That is, it's usually not just one or two compounds, but a whole bunch of compounds that make up the overall complex flavor profile. In addition, certain compounds may be a natural part of one product's flavor profile, but an undesirable part of another. So for instance, think about a strong cheese, a blue cheese or a goat cheese. These cheeses have a very strong, distinct smell and flavor associated with them. And this is a key part of that product's identity and is desirable for that product. But if you were to take some of those intense aroma compounds and associate them with something like a chocolate chip cookie or perhaps a saltine cracker, you would get an off odor. So because of these two factors, that is the complex nature of most products, as well as the fact that some compounds may both be desirable in some products and undesirable in others, one of the most definitive methods for identifying off-odor causing compounds is by comparing a good sample, that is a sample that is supposed to be the same flavor, that does not have this issue, to the complaint or off-odor sample. And so by doing this, we can look for compounds that are present in the complaint sample and not in the control sample. And this can be indicative of, say, contamination or microbial growth, and can lead us to the source of the off odor. And the reverse can also be beneficial. That is, looking for compounds that are present in the good or the control sample that are not found in the complaint. And this can be indicative of, say, an issue in processing. Maybe a key ingredient or a key flavoring compound was not added or not added in appropriate amounts. And so now you're getting a change in your flavor profile. And so it's all well and good to talk about volatile profiles and aromatic profiles, but how do we go about actually detecting and identifying these compounds? That is, what is our scientific approach to this problem? And so we do our off odor and off flavor profiling using a technique known as gas chromatography coupled with mass spectrometry, or GC-MS for short. And GC-MS is a powerful technique and our flagship approach for the analysis of volatile profiles. How this approach works is compounds are volatilized and then separated in a gas phase based on their affinity to the stationary phase. This is the gas chromatography portion of the technique. And we can tailor this approach to different classes of compounds depending upon the potential source of the off odor by changing factors such as the stationary phase or the GC column, as well as factors such as temperature profiles, gas flow rate, and so on. And so we can tailor this approach to our particular products. However, once these compounds are separated, we need a way to detect them. And we do this using mass spectrometry. And mass spectrometry is a powerful tool for this approach, as it not only has low limits of detection, but it also allows us to identify the compounds that we see. And we are able to use mass spectrometry for identification based on characteristic fragmentation patterns. So GC-MS uses an ionization technique known as electron impact. And this results in the production of fragmentation patterns. That is, we take these compounds and they're broken down into smaller pieces. And the way these compounds break down is characteristic to each structure. So by taking that fragmentation pattern, we can compare it to our library of compounds and identify it. And we have libraries of over 300,000 compounds that allow us to identify a wide variety of different chemicals. And in addition to standard single mass spectrometry, we also have capability for tandem mass spectrometry, or MS-MS for short. So with single mass spectrometry, what we're looking at is an untargeted method. In this approach, we ionize and fragment all analytes and detect all the fragments that we see. In this way, we can scan a product to see what is present and identify our unknowns. However, in some cases, if we want to be a bit more selective and targeted, we'll use tandem mass spectrometry. An MS-MS filters ions of interest into a collision cell where they are broken down further and then further filtered by product ion. And this allows us to have increased selectivity and sensitivity. So as you can see, an example here of a fragmentation pattern of a compound as determined by mass spectrometry. And then using MS-MS, we can specify, we're going to look at the 1241 ion, which is then fragmented to the 681 ion. And this is highly beneficial for trace analysis of known compounds. So as I mentioned, using MS-MS, we can greatly increase sensitivity for target molecules even in a complex matrix. And this is ideal for monitoring specific compounds. So say, for example, you're concerned about contamination with a pesticide or a cleaning agent. Maybe you've done some previous analysis and know that this is the source of an issue that you want to monitor. By using MS-MS, we can specifically target that compound of interest. So as I said, MS-MS is an excellent option for sensitive target analysis, while our general mass spectrometry single quad is best for untargeted work, such as most off-odor investigations. So I've talked a bit about how we separate compounds and then how we detect and identify them. But before we can do any of that, we have to sample these volatile compounds. That is, we have to get them from the product into the gas chromatography system. And there's a number of ways of doing this, but our most powerful approach is known as solid phase microextraction, or SPME for short. And SPME is a technique for the selective extraction of volatile components from a sample. And the way SPME works is we use fibers coated with a thin layer of polymer material. So this polymer material acts as an extracting phase, allowing for this selective extraction and concentration of volatile compounds. This is highly beneficial as it allows us to extract volatile compounds away from the less volatile portions of the product, say your proteins or your long-chain carbohydrates such as starches, which can help us reduce matrix effects of these complex samples. As well, SPME gives us increased sensitivity as we can concentrate these volatile compounds before we do our analysis, allowing us to see even lower limits of detection. In addition, we can also target this approach. So we can select fiber coatings based on the compound classes of interest. And there are a variety of commercially available SPME fibers, including traditional SPME fibers, which I have an image of here, as well as the new SPME Aero, which has an even thicker layer of polymer material, which can allow for even greater concentration effect. And so for SPME, how we approach SPME is we incubate samples in Headspace files in order to release volatile compounds, as we want to get as many of those into the gas phase as possible. And we can select or adjust our temperature based upon the sample of interest. So say something that is highly volatile, has a strong aroma to it, we will use a lower temperature than something that has a weak aroma. After the vial has been incubated, we will expose the SPME fiber to the generated headspace gases and allow it to equilibrate, giving time for those volatile compounds to adsorb to the fiber surface. Following this, any absorbed compounds are then thermally desorbed into the GC inlet and analyzed by GC-MS. And in addition to fiber coating and time and temperature of incubation, we can also change or adjust the selectivity of this method by changing factors to do with the sample. That is, we can add saturated sodium chloride solution or change the pH of a product to improve the volatility of the compounds of interest. In addition to SPME, there's a number of other approaches for our GC-MS analysis. Another common approach we can employ is known as Headspace-GC-MS. And Headspace-GC-MS is useful for highly aromatic products where the concentration effect from SPME may not be desired. So some products that have a very strong aroma might show too much concentration with SPME and overwhelm the system, resulting in poor separation and identification. In these cases, instead we would use Headspace-GC-MS, where we sample an aliquot of the unconcentrated headspace gas. So that's just kind of a brief overview of our approach to off-odor and off-flavor analysis. Now we want to talk about some case studies. These are examples in real-world complex matrices, and I hope to give you some idea of how this approach can be employed and what kind of information we can glean from this. So for now, I'm going to turn it back over to Lily.
Thank you, Dr. Willems, for that introduction. So today we're going to start with a case study looking at chocolate sauce investigation. So a food manufacturer noticed an off odor in chocolate sauce after they began manufacturing with new equipment. So they sent us a sample of the suspect batch that didn't smell correct, and they also sent us a control batch from before they had started using the new equipment for comparison. So what we're looking at here is the chromatographic aromatic profiles of the two samples. So on top in pink, we have our suspect sample, and on the bottom in black, we have the control sample. And you might notice these have extremely complex profiles. There are many different volatile components that are important in creating the aroma of a chocolate sauce. So each peak here is a different component, and as Dr. Willems described, the beauty of the mass spec detection is that each of these components, each of these peaks, has actually been identified by the mass spec by comparing those fragmentation patterns to libraries. So we have a huge amount of information just looking at these overall aromatic profiles, and when we have something this complex, to narrow in and really try to find the source of an off odor, we sometimes have to look very closely. So to start with, we're zooming in on this early chromatographic section. So the first thing we noticed is we identified this peak. This is found in the suspect and not the control sample, and this was found to be diacetone alcohol. And looking later in the chromatogram, we also identified tetramethyldecyindiol, which was also found in the suspect and not the control sample. So these two compounds were identified in the suspect and that were not present in the control, and they also have many different potential industrial uses. So diacetone alcohol is a solvent. It can be found in many different coatings and adhesives, and it's known for having an acetone-like or ethereal odor. And tetramethyldecyindiol is a surfactant. It can be found in inks, adhesives, and waterborne coatings and similar. types of things, and this is known for having more of a menthol-like off odor. So in this particular case, these volatiles that we identified in the suspect are unlikely to be the source of the off odor in and of themselves. So in this case, they likely indicate the presence of contamination that has other less volatile components, and these two components might just be the most volatile components of the off odor contamination. So our next case study, where we were looking at a vanilla-flavored beverage. So this was a sort of dairy-based vanilla drink, and it was suspected to have spoiled. So we received samples of this suspected spoiled batch along with samples that were unspoiled. So the first thing you might notice in these profiles is that they are a lot less complex than our chocolate samples. This isn't unexpected since this beverage had a fairly mild vanilla aroma to it, so we would expect a much less complex profile. So once again, on top we have the suspect in pink, and on the bottom in black we have our control. So one of the first things we noticed, on the left we have these two peaks, 2-ethoxyphenol and guaiacol, and what we noticed is that we have more of these two compounds in the suspect than in the control. Later on in our chromatogram then, we have piperonal, ethylvanillin, and vanillin, and in this case we actually had less of these compounds found in the suspect than in the control. So after we got this information, we had to then dig deep and figure out what could this actually mean, and how does this impact the overall odor of our actual samples. So we found that the main odor components of vanilla are actually our three main peaks that we saw previously, which are the vanillin, ethylvanillin, and piperonal. The other two elements that we identified are actually industrial precursors in the production of vanilla. So these two compounds are precursors that were potentially incompletely reacted. So in this case, the vanilla in the suspect beverage may have been degraded, or it may have had a problem during production, which is what led to this off odor. So in this case, we had an ingredient issue. And now I'm going to hand it back to Dr. Willems just for a few case studies.
So thank you, Lily. For this case study, we're going to be talking about a table sugar investigation we did. So I'm talking about table sugar, I'm talking about pure sucrose. So as you know, table sugar doesn't really have a strong aroma associated with it. So when our client got a complaint from a customer, they were concerned. So the customers complained of a powerful soapy aroma in their table sugar. And when we received the sample, the complaint sample, indeed it did have a very strong aroma associated with it, almost floral-like in nature. And so we received this complaint sample alongside a control sample from the same batch that the processor had retained. And so we analyzed these samples of both the control and the complaint product for their volatile profiles by our SPME-GC-MS approach. And so on this slide, I have the chromatograms of the control sample on the bottom in black, and the complaint sample, or the off-odor sample, in pink on the top. As you might expect, in the control, there wasn't very many peaks. That is, there wasn't a lot of volatile compounds associated with this product. However, when we looked at the suspect sample, we saw a variety of peaks indicating the presence of components that were not in the control. And we were able to identify a lot of these. For instance, these peaks here were identified as solvents or related compounds, such as acetic acid, as well as a variety of different glycol-related products. As well, we also identified a number of fragrances. These are reported to have floral-like fragrances. And so, as I mentioned, the suspect's sugar sample was found to contain abundance of compounds not found in the control, including these glycols as well as fragrance agents. And many of these compounds are known to be common ingredients in a variety of products, including cosmetics, soaps, detergents, and cleaning products. And the presence of acetic acid, along with some of these other compounds, suggested a cleaning product. And so this suggested that the complaint sample had been contaminated. And using this information, the processor was able to go back to the customer who made the complaint. And the customer said that they had been storing their table sugar open on the counter next to their sink, where they would often do dishes. So in this case, What was happening is the customer themselves had contaminated their sugar, and it was not an issue in production or transportation. That is, the processor didn't have an issue, and they were able to close out this investigation. Okay, so in another case study, we looked at a dietary supplement. This was a protein-like powder or a protein powder. For instance, think of something you might consume after a strong workout that is commonly sold in bulk. And so we received a complaint sample where a powdered dietary supplement that had a wet cardboard or barn-like off odor. And in this case, the client, the processor, had caught this complaint before it had been shipped out. So they were able to keep it in-house and didn't have to worry about recalls or customer complaints. And so we examined this off-odor sample alongside control samples from a previous batch that did not have this off-odor. So here on this slide, on the bottom, I have the volatile profile of the control sample in black, and on the top, we have the suspect sample in pink. And we noticed a number of key things. For one, we were able to identify a number of compounds that were present in the suspect sample and not found in the control, such as 1-pentanol, propanoic acid, and pentanoic acid. In addition, we saw elevated levels of other compounds, namely hexanoic acid and hexanol. And a lot of these compounds, that is pentanoic acid, hexanoic acid, propanoic acid, are what are called short-chain fatty acids. And the presence of these compounds, alongside the presence of elevated levels of hexanol, can be signs of the oxidation or breakdown of lipids and have fatty, cheesy, or goaty odors, which led to that barn-like smell. In addition, hexanol has been reported to have a cardboard or a wet cardboard-like aroma. And so by identifying these compounds, we could identify what was causing the off odor. And so after further consultation with the client, the source of the fatty acids was identified as a byproduct from an issue in processing. So basically what was happening was there was a defatting step that wasn't going to completion. And so the product was retaining higher amounts of fat than normal. And then during heating later down in processing, these fats were breaking down into these free fatty acids, causing the off odor. So by fixing their defatting issue, they were able to correct and prevent this off odor from forming in the future. So now I'm going to turn you back to Lily for the remainder of this presentation.
Thank you, Dr. Lilly. So our next case study is looking at some bottled water samples. So complaints were received about an off taste and off odor in bottled water that was described as very chemical-like and sharp. So we received samples of these complaint samples along with control samples for comparison. So what we found for that, there were an assortment of benzene derivatives in the complaint sample that were not found in the control, and these included things like ethyl dimethylbenzene along with tetramethylbenzene. So when we investigated these types of compounds that were in our suspect and not in our control, we found that these types of benzene compounds have a wide range of potential industrial uses, such as dye formulations, gasoline, resins, and also adhesives. And in addition, these compounds are known for having very sharp phenolic-like odors. So in this case, it appeared that these problem bottles of water had been contaminated with some type of an industrial solvent. However, this was not the end of the story for this particular investigation. So using this information, the client investigated their own processes, and they found that they had begun using a different tank with a different interior coating since the issue had started. So they actually sent us samples of the actual coating material from the inside of these tanks, and we were able to test it in the same way that we tested the bottled water samples, and we verified that the coating did contain many of these modified benzene compounds. So by going through this process and then looking at their own processes, the client was able to track down the exact cause of this problem and prevent it from happening in the future. Our next case study was looking at a fruit drink beverage. So in this case, the suspect sample was described as smelling differently than the control. So in this case, it wasn't actually described as an off odor, but it didn't smell like all of their previous batches had smelled. So once again, we have our suspect on top in pink, and on the bottom we have our control in black. So the first thing we noticed was that these two major components, these large peaks here, had different intensities. So limonene on the left was found in lower levels in our suspect than our control, and terpineol on the right was found in higher levels in our suspect than our control. When we zoomed in closer, since there are many different components of these profiles, we found more differences. So we saw less of myrcene and decanol in our suspect, along with increased levels of hexanol, isoborneol, and carvone. So when we investigated what this could actually be pointing to, we found that all of these compounds are potentially important in different fruity odor and flavor profiles. So for example, hexanol is commonly found in apple odors or flavors, while limonene is found in most citrus flavors. So in this case, we didn't find any evidence of contamination. We didn't see any components that would point to some sort of soap or anything like that, as we had seen in previous cases. So what this actually pointed to in this case is potentially an incorrect amount of a flavoring was added to the suspect sample, which led to that overall different odor profile. So this was once again an ingredient issue. Our next case study is flavor scalping. So as Dr. Willems described earlier, flavor scalping is a phenomenon where the packaging of a product absorbs flavor compounds over time, and this can result in reduced aroma intensity or a change in the overall aromatic profile. So what we have here is a theoretical example of what flavor scalping could look like. So in red, we have a profile of a spice, and then in black, we have a profile of what that spice might look like under circumstances where it was in packaging that were then scalping different compounds. So one thing you might notice is that different peaks do not appear to be impacted. For example, towards the end of the chromatogram, these compounds actually look like they are still there in the same levels. On the other hand, many of the compounds earlier in the chromatogram, say around 17 minutes, are severely impacted, so you see much less in the black profile than in the red profile. So this wouldn't be unexpected, since different compounds would interact differently with the packaging. So this is just to show you what we might actually see if we were investigating a flavor scalping situation. Our final case study today is flavor profiling of bacon. So in addition to off-odor analysis, GC-MS can be used for general flavor profiling. This allows us to do comparative analysis between similar or different products, and it can be also used to determine the impact of processing, ingredients, or storage on the flavor profile of a product. So if you think back to the chocolate sauce profile that we showed earlier, there was a huge amount of compounds that were involved in creating that aroma. So that was in itself a vast amount of information about the actual profile of that product. In that case, that isn't what we were most interested in, but we can use this amount of data to really understand what creates the profile. So what we have here on top in red is the profile of a rendered fat broth that was created from a cooked bacon product. And the cooked bacon product profile is found on the bottom in black. So you might notice there are very complex profiles for both. There are some similarities along with many differences. So when we really looked closely at these profiles, I'm going to highlight some of the differences that we found. So these orange arrows are pointing at compounds that are known to incorporate sweet odors or flavors. So as with the orange arrows, we're seeing primarily these compounds being more abundant in our bacon. And then blue arrows here are pointing at fatty or acidic flavors. So we're seeing more abundance of these in our rendered fat broth product. And the final thing I'm highlighting here with green arrows, these are compounds that contribute roasted or caramel-like flavors and odors. And once again, we're seeing more of these in our bacon than in our broth. So the bacon and broth did share a number of volatiles. As I said, this included things such as acetic acid, butanone, and 1-hydroxy-2-propanone. But we also saw many differences, including more sweet and buttery aromas and roasted odor compounds in our bacon sample, along with higher proportions of components that are known for having fatty flavor profiles in our broth. So in this case, we identified many different profile differences, and this just helps our client to understand why this broth that they had created from the bacon wasn't really incorporating the actual bacon aroma. So when we do off-odor analysis, there are some additional techniques we can employ, and there are some additional techniques we can employ, and one of these, as Dr. Williams described, is GC-MS. So after we do an overall profile using GC-MS, we can use GC-MS for increased sensitivity and selectivity. So if we narrow down to a specific compound that we're interested in, and we want low-level quantitation where we can detect this compound at extremely low levels, then we can hone in on it using GC-MS. Additionally, we have other complementary approaches. These include metals analysis. If we don't find something different in profiles during off-odor analysis with GC-MS, sometimes we turn to metals analysis, since metals can be a source of off-odors in different products as well. We can also do microbial analysis if we suspect fermentation or other types of bacterial growth. And in this case, then, we can confirm and ID potential microbes that might be causing the problem. So in summary, SPME, GC-MS, and GC-MS are powerful techniques for off-odor analysis along with volatile profiling. By comparing the profile of a control and suspect sample, we can identify compounds that are responsible for the odor and hopefully identify what this could potentially be caused by. As we showed today, these off-odors can come from many different sources, including contamination, ingredient issues, spoilage, flavor scalping, and even processing issues. And these can be on the industrial side or on the customer side. So SPME GC-MS is very versatile, and we are always looking for new ways to employ these techniques to help our clients achieve their goals. So thank you for tuning in today, and we'd be happy to take questions now.
All right, thank you so much for the presentation. As Lily mentioned, we will move into a short Q&A. Feel free to continue to submit your questions. I see a lot of good ones coming in through the chat. And just as a reminder, we'll take a few questions here I'll be asking, but if we don't get to them, we will respond to you offline. So the first one that came in here is, how difficult and time-consuming is it to volatilize and separate compounds?
Right. So thank you for the question. It depends on your product. With the volatilization, usually what we're doing is we're incubating a sample at different temperatures. So for low volatility compounds, often we'll need longer times and higher temperatures. But for samples that have a lot of aroma associated with them, we'll need shorter times and lower temperatures. And then separation is similar. If we have a lot of compounds in there, this can get quite complex, and we might need to try multiple columns or different temperature profiles in order to get good separation.
Okay, wonderful. Thank you. The next question comes in, what is the standard way that you use to prep samples for SPME GC-MS for off flavors? And is it matrix dependent?
Sure. So once again, it is sort of matrix dependent in the sense that each sample is going to be different, and each sample we have to treat based on what we know about it. So in many cases, if we have a dry sample, we will prepare the sample as is, so we will just weigh some of that sample into our vials and analyze it to see if we can get good results that way. A lot of times at the same time, we will prepare a sample with the addition of sodium chloride, as Dr. Williams described, which can help promote volatilization as well. On the other hand, if we have a liquid sample, we could also add that to the vial and approach it in the same way. And we can also adjust the pH. Sorry, interrupt.
Oh, no, thank you for that. Excellent. And then this question is in reference to the first case study. In the first case study, do the peaks in compounds align with a lubricant or compound found on the new equipment? And how would one correct or eliminate the compound from the new equipment to continue to produce the chocolate sauce?
So the peaks and compounds we found in the chocolate sauce were matches to kind of a coating or a lubricant that was likely used during the production of this equipment. So a little bit of background is this was new equipment that they had just started using. And so what we found were markers for the indication of the presence of a lubricant. The best way to correct this would be likely to flush and clean out the processing equipment, as they actually saw over time with more batches that this problem became less and less apparent, that is, the off odor reduced over time.
Okay, great. Thank you. And then you mentioned you identify compounds by comparison of mass spectra to libraries. What sort of libraries do you use?
Sure. So we have access to several mass spectral libraries, including the NIST, main, and Wiley flavors and fragrances spectral libraries. Both of these are very useful for this type of analysis. And generally speaking, the fragmentation obtained by GC-MS is very consistent across different instruments and method parameters. So these databases can be applied to many different types of analyses, including our off-odor scenarios.
Great, thank you. And what type of statistics do you recommend for comparing control versus suspect profiles without peak identification?
So generally, we rely fairly heavily on peak identification, but what we do in our analysis is all our samples are run at least in duplicate, so we can have replicate information to know kind of the variability between sampling, and then we compare our control to our suspect sample, looking across, for instance, a peak area, whether or not a peak is detected in the first place. And so by doing this, we're able to identify compounds that are likely sources of the off odor. If we want to get more specific with quantitation, then we require further work to get specific concentrations.
Great, thank you for that answer. And do you have a favorite SPME needle for off flavors?
Well, our sort of go-to SPME fiber is a divinylbenzene carboxane on a polydimethylsiloxane fiber. It's also known as the gray fiber when you look at the color coding. And this is our sort of go-to fiber for volatiles and semi-volatiles. We typically do start our analysis using this fiber, and then if we suspect that we aren't getting good results or that we want to investigate a different type of compound more seriously, then we will change our fiber from there.
Wonderful, thank you. And this one is asking, are techniques incorporated into food safety plans or preventive controls, such as consumer complaint or recall plans?
So generally, what we do here is we're doing kind of investigative analysis. We're kind of the emergency room per se. So something has gone wrong, and we're helping to find out what that is. After a potential problem has been identified, then a client can start to think on, okay, so how can we monitor this? Do we continue with GC-MS? Are there other techniques available for monitoring for this issue?
Wonderful. Okay. And there's many good ones coming in here. I think we'll address just a few more here. So for complex matrices in an off-odor investigation, such as meat, how many samples would be required for this analysis to establish a good profile?
So at least what we want to see, usually when we're talking especially complex matrices, is we want to see at least one control that is as close to the suspect as possible. So if you have, for instance, like I talked in the sugar profile, a control that was the exact same batch, that is ideal. For something complex like a meat, we might need a couple because, animals vary. But the closer the control is to the suspect, often we can use a single control and a single suspect.
Wonderful, thank you. And all of the case studies described the approach of comparing a control versus suspect sample for off odor, off flavor analyses. But what approach is taken if a control sample can't be provided?
So in this case, we can do our best to analyze, and we can still get a lot of information from the volatile profiles. In some cases, a contamination may still be obvious depending on what type of compounds we are seeing. However, as Dr. Willems described previously, when we don't have a control, it can be very difficult to determine what compounds are supposed to be there and what aren't. since some, as she said, can be good in some cases and be the source of the off odor in others. So we can investigate as well as we can if we don't have a control, but it is definitely ideal for the best results if we do.
Wonderful. Thank you so much. And we are nearing the top of our time here to conclude on this session. Again, more questions are coming in, but we can address those offline. I just want to remind everyone that a recording of this webinar, along with a copy of the slides, will be available in 3 business days. And I want to thank Jamie and Lily again for sharing your presentation and expertise. And thank you again to everyone for attending today.